Which region of the periodic table shown here contains the most readily oxidized elements? Well, the easiest ones to take electrons off of are the metals shifted all the way to the left. So that'd be A. Which region contains the most least readily oxidized elements? All right, so again, the more I go to the right, the harder elements hold on to their electrons, the higher the electronegativity. So the hardest elements to take electrons away from are all the way over to the right. Determine the oxidation number for the indicated element in each of the following substances. All right, so S in sulfur dioxide. So we go to our rules in terms of oxidation state, and one of our major rules says for oxygen it's always -2. So if you have two -2 oxygens, that must mean the sulfur is +4 in order to have a electrically neutral compound. The carbon in COCl2. All right, so the oxygen's always -2, and in this case, the chloride would be usually -1, especially if it's connected to that carbon, and that's the way this molecule would be. Lose 1, lose 2, lose 3, lose 4, again, +4 for the carbon in this compound. The manganese and potassium permanganate. Again, we can look at permanganate, MnO4- by itself. You've got 4 oxygens adding up to -8. So the manganese would have to be +7. The bromine in hypobromous acid. O would be -2. The H would be +1. So the bromine would be +1. Arsenic with 4, right? So this is just elemental arsenic. So 0. The oxidation state of elements, they haven't lost or gained electrons, is 0. Oxygen in potassium peroxide. All right, so peroxide is an ion that's different. Most of the oxygens we run into, it's always -2, but in this situation, potassium can only lose 1 electron, so you've got 2 of them, which adds up to a +2. So that means each of the peroxides would have to be -1. So that's how you rationalize the oxidation state of peroxide. Looking at 57, the metal cadmium tends to form a +2 cadmium ions, +2 charge. The following observations are made when a strip of zinc metal is placed in cadmium chloride. Cadmium metal is deposited on the strip, all right? So that means cadmium 2+ is able to take electrons away from the zinc metal. So looking at the net ionic equation, right, the chloride is just there as a spectator in the situation. This reaction is about cadmium 2+ taking electrons away from zinc. Write the net ionic equation for the reaction. Explain let's do the next one, right? So that's 1. 2, a strip of cadmium metal is placed in nickel 2 nitrate, all right? So nickel 2 is the oxidizing agent here, and nickel metal is deposited on the strip, all right? So nickel 2 can take electrons away from the cadmium. So nitrate's a spectator here. This should be about cadmium. This reaction is about cadmium giving up electrons to nickel 2 to form nickel metal and cadmium 2+. B, what can you conclude about the position of cadmium in the activity series? All right, so looking at the activity series, right, whatever metal cation is below the metal on the chart, it can take an electron. So zinc can lose electrons to the cadmium 2+. That must mean it's below it on the chart. And the nickel 2 can take electrons away from the cadmium metal. So cadmium must be in between, like around iron somewhere. in terms of this activity chart. So it can take electrons away from the zinc, so that makes it lower than zinc metal, and cadmium metal gives up electrons to nickel 2+, so that means it's above it on the chart. Write the balanced molecular and net ionic equations for the following reactions. Identify the gas formed in each. Solid calcium sulfide reacts with an aqueous solution of sulfuric acid. All right, so we've got calcium sulfide reacting with an aqueous solution of sulfuric acid. That's going to form hydrosulfuric acid, or hydrogen sulfide and cadmium sulfate. All right, and so this would be the molecular equation. All right, so it's balanced. And what I would look for in this situation is any spectator ions. So in the situation with sulfuric acid, right, it's the weirdo acid. It's the only strong acid that's polyprotic. And it's a strong acid because of the first H, not the second H. So if I'm looking at the ionic equation for sulfuric acid, that H is detached from the hydrogen sulfate. And both H's go on to that sulfide to form hydrosulfuric acid and cadmium sulfate. So there is no spectator here. This would be the ionic equation for this reaction. Solid magnesium carbonate reacts with an aqueous solution of perchloric acid. All right, carbonate's weird. Later on, we're going to talk about how carbonate can act like a base. But with carbonate, when it reacts with an acid, what you form is carbon dioxide gas. So carbon dioxide and water come out along with perchlorate and magnesium ion. So in this situation, the gas is carbon dioxide. So I've got 1 carbon, 3 oxygens, it's balanced. If I'm writing the net ionic equation for this, again, perchloric acid is a strong acid, so that H is detached. This would be the molecular equation. So with the 2 moles of perchloric acid, those H's are detached from the perchlorate. Perchlorate goes in the same way it comes out. It's a spectator ion, so it's not involved in the reaction. So this reaction is about the acid reacting with the carbonate to form carbon dioxide and water. Magnesium ion is liberated, right, when that solid is pulled apart, so it's a product. This would be the net ionic equation. All right, C, what experiments would you need to perform to locate more precisely the position of cadmium in the activity series? All right, so it was somewhere in between nickel and zinc. So it was more towards iron, right? So we'd want to know how whether cadmium 2+ could oxidize iron or cobalt or chromium, right? And then we could get a better gauge as to whether it was a better cadmium 2+ is a better oxidizing agent than iron 2+ or chromium 2+ and so on. So, I guess we've already shown you what 59 is, right? A concentration of solution. Is the concentration of solution an intensive or extensive property? Extensive properties have to do with amount, right? So this means that if it's a ratio, like how many moles you have per liter, then it's an intensive property. So when you talk about 0.5 moles of hydrogen chloride or hydrochloric acid, you're talking about an amount. If you're talking about 0.5 molar, you're talking about a ratio of how many moles per liter you have. All right, so it's amount independent. You could have a few drops of 0.5 molar solution or a gallon of 0.5 molar solution. 67, calculate the number of grams of solute, all right, when you have 0.25 liters of a 0.175 molar potassium bromide solution. All right, so this is the new conversion unit, right? It's a ratio of moles per liter. So we can use this as a way to go from liters of solution to moles. right? So put what you want to cancel out of in the bottom, multiply across, and we get to moles potassium bromide, and once we're moles, we could use the molar mass to get to grams. So this is our new conversion unit in this topic, right? Molarity. B, the molar concentration. The molar concentration of a solution containing 14.7 grams of calcium nitrate in 1.37 liters. All right, so if they give us grams, we can use molar mass to get to moles of the solute, and then divide by liters to get the molarity. Okay, so how many moles of solute do you have per liter of solution? C, the volume of 1.5 molar sodium phosphate in milliliters that contains 2.5 grams of solute. All right, so with all these guys, what you want to do is write down what you're given, right? You're given 0.25 grams of the solute. So use that as a convert out of it, right? I want to get out of grams and get to something else. Well, the only thing we can do at this point to get out of grams is either use density or use the molar mass, right, as a way to get to moles of sodium phosphate. Now that I have moles of sodium phosphate, I can use that conversion unit, 1.5 molar, right? It's moles per liter, so put moles in the denominator, liters up in the numerator. You've converted to what the volume of the solution would be. Then convert to milliliters, using the definition of milliliter. So if you have this many grams of this many molar concentration, you've got 10.2 milliliters of solution. 75. Starting with solid sucrose, describe how you would prepare a 250 milliliter 0.25 molar sucrose solution. All right, so if you're given milliliters, that's what's given here. Use the molarity to convert to moles. And once you've got moles of sucrose, you could use the molar mass to figure out, how many grams you'd need. B, describe how you'd prepare a 350 milliliter 0.1 molar sucrose solution, starting with 3 liters of a 1.5 molar solution. All right, so this is a dilution problem, right? So we have a concentrated solution, a 1.5 molar solution, and we have 3 liters of it, and we want to describe how we're going to prepare our ending volume is 350 milliliters, and we want a 0.1 molar solution. So that's my V2 and my M2, and I'm starting with a 1.5 molar solution. So what I want to know is how much of that 3 liters am I starting with? I mean, how much am I going to use of that 3 liters to dilute to 350 milliliters to get that 0.1 molar solution? So I plug into the equation, right? I want to end with a 0.1 molar solution, and I want to end with 350 milliliters, which is 0.35 liters. So the question is, what's the volume I'd have to start diluting with to get that 350 milliliters? And it's 23.3 milliliters. So if I put 23.3 milliliters in my graduated cylinder and dilute up to 350 milliliters, I'd have a 0.1 molar concentration. What mass of potassium chloride is needed to precipitate the silver ions from 15 milliliters of 0.2 molar silver nitrate solution? All right, so again, we're given milliliters of a 0.2 molar solution, so I can use the volume, right, convert to liters, and then use the molarity to convert to moles. And what I want to do is figure out, I want to be able to go from moles of silver nitrate to moles or grams eventually of potassium chloride. So according to the equation, for every 1 mole of silver nitrate getting used up, using up 1 mole of potassium chloride, and now I can use the molar mass to get 2 grams. So stoichiometry involving solutions, right? The new thing is just a new way to get to moles, right? Once we've gotten to moles, then it's about using the coefficients in the balanced equation to go from moles of one thing in the equation to moles of another, and then get to the quantity I want to get to, which in this case was grams. Some sulfuric acid is spilled on a lab bench. You can neutralize the acid by sprinkling sodium bicarbonate on it and then mopping up the resultant solution. The sodium bicarbonate reacts with the sulfuric acid as follows. Sodium bicarbonate is added until the fizzing due to the formation of CO2 stops. If 27 milliliters of 6 molar sulfuric acid was spilled, what is the minimum mass of sodium bicarbonate that must be added to neutralize the spill? All right, so we have a balanced equation. We have milliliters of a certain molarity of sulfuric acid. So we write down what we're given. We're given 27 milliliters. If I convert that to liters and then multiply by the concentration, I convert to moles of sulfuric acid. So now that we're in moles, we can use the mole method, right, to convert from moles of one thing in the equation to moles of another. For every 1 mole of sulfuric acid getting burned up, 2 moles of the sodium bicarbonate getting burned up, and then I can use the molar mass of sodium bicarbonate to get 2 grams. So the only thing new with this stoichiometry problem is that if you're given liters and the molarity, you can get to moles, and then it's just using the coefficients to get to moles of one thing to moles of another in the equation.